Well, I did it again. I kind of jumped ahead of myself, and this next section, 37.7, actually addresses the 4 momentum vector. And you recall that we just did some of this 4 momentum by saying, here's the 4 velocity, and the 4 velocity is c times dx dt. This d tau is actually the clock that sits on the particle, and you have to differentiate with respect to it, because it turns out that this clock is the same to every observer, whereas ordinary time transforms among observers in different ways. Now this 4-dimensional velocity, when multiplied by mass, gives us our 4-dimensional momenta. And from the 4-dimensional momenta, we can take the length of it and find that it's equal to m squared c squared. We see that explicitly when I define this p mu as mass times v mu, which is what I just did. Then I form this scalar product, which gives p naught squared minus p1 squared minus p2 squared minus p3 squared, because this g, called the metric of the space, has the diagonal values of 1, minus 1, minus 1, minus 1. And so we write the energy out exactly as before, and therefore by doing this we can see that E squared minus px squared, or minus p squared in general, is equal to m squared c squared, or this equation here, which we were previously studying for the relationship between mass and energy and momentum. That replaces our E is equal to p squared over 2m, which is valid in Newtonian mechanics. So, all in all, we have gone from a concept of position, of time, where time in a new frame was equal to time in the old frame, a position which was always related in a simple way to other positions, and x minus velocity times time for something that's moving, and then a plane velocity, which was change in x over change in t, which was the same in both frames, an acceleration, which was the change in velocity, and let me go on to the momentum here. Momentum is mass times velocity. Well, now we have changed this, and we realize that all of these are now connected in one vector, x naught, which is ct, x1, which is x, and x2, which is y, x3, which is z, and these 4 pieces of position called x mu, where mu goes 0, 1, 2, 3, are the 4 components of space and time for some event that happens. Likewise, we can take the length of this infinitesimally and define a d tau, an infinitesimal change in tau, as the square root of dx mu dx mu. And that gives us this invariant time that can now be used to differentiate and form a new kind of velocity. V mu is change in x mu over the change in tau, where tau is a scalar value because it's the length of a scalar product. And where p mu, we need a c there, recall, in order to give it the right units. And p mu is then m times v mu, which is also mc times dx mu d tau. Now, this is just a very brief introduction to some of the more difficult aspects of special relativity. You can see that what you really need here is matrix theory. You need to be familiar with the hyperbolic functions. And this is a new concept, a scalar product, that's not just like the Pythagorean theorem, but it says that something new is invariant. This new thing that's invariant is not the square root of x squared plus y squared plus z squared, but this d tau is the square root of dx naught squared minus dx1 squared minus dx2 squared minus dx3 squared. So it's different from the Pythagorean theorem, and this is called an indefinite metric. meaning that things can have a zero length even though these vectors are not zero. So special relativity is not just as simple as just the Lorentz contraction and so forth, but takes us to a new depth. And this new depth is something you have to grasp